Okay, so today we're going to be learning about zeros of polynomial functions. Now the first thing I want to say is that anytime you see the word zeros, remember zeros just means x-intercepts. So if a question ever asks you, what are the zeros of this graph, it's just asking you what are the x-intercepts of the graph. They're synonyms. So last class we learned about polynomial functions and their zeros, specifically how we can look at a sketch of a graph and come up with an equation to model this. So this first example is just a review example from what we did last class, and I'll go ahead and do this one with you guys. So let's say we have this polynomial function that's graphed for us, and we want to come up with a possible equation that would model this. Now we're given the graph, and we somehow have to come up with an equation. Now the first thing that we do for dealing with polynomial functions is we locate the zeros or x-intercepts. Now there's a total of 3 of them. And I've already kind of labeled them for you. So since there's 3 x-intercepts, what I'm going to do is I'm going to create 3 sets of parentheses. And in each parenthesis, I'm going to kind of put the template x minus. It doesn't matter which x-intercept you start with. I'll go ahead and start with this one. This one's 1, so it'll be x minus 1. This second x-intercept is -1, so it'll be x minus -1, which would just turn to a positive 1, so I'll just put +1. And this last x-intercept is -3, so it'll be x minus -3, which would just become x plus 3. Now, you would look for any bounce backs, but there are none here, any multiplicity. If you look at the graph, every single point crosses to the other side of the x-axis. So for example, if I start at -3, the graph was below the x-axis and now it's above it, so there's no multiplicity there. Once I get to -1, the graph was above the x-axis and now it's below it. So it crosses to the other side of the x-axis. Once I get to +1, the graph was below the x-axis and now it's above the x-axis. So there's no bounce backs. It's crossing to the other side. So we don't have to worry about any multiplicity or special exponents. So this would be our equation. You could multiply this out. You could FOIL all of this out. This isn't wrong. If you wanted to, you could FOIL x times x, which gives us x squared. X times 1 is positive 1x. -1 times x is -1x. -1 times 1 is -1. And we still have this x plus 3 I haven't worked with. And you could combine like terms. If you notice, we have a plus 1x and a minus 1x. That'll cancel out. It's just 0x. And we have x squared minus 1, and then we would still have to FOIL it by the x plus 3. We have to multiply everything by everything. So then I would multiply x squared times x, which is x cubed, x squared times 3, which is 3x squared, -1 times x is -1x, and -1 times 3 is -3. And there's no like terms, so we can go ahead and leave it as is. And there's our equation. It's not wrong if you leave it in factored form, but just know that this equation is also correct. These are the same equation. I just multiplied everything out and simplified it. So this first equation would have been fine as well. Just want you to know it can be written in factored form or in FOILed out form, either way. So that's what we did last chapter. Okay, so today I'm going to kind of jump around on these notes just so I kind of have put a few questions out of order, and that's fine. For this next part though, and I'll bounce back to this, is that we can have a bunch of different types of x-intercepts. It's nice whenever the x-intercepts are whole numbers like 1, -1, and -3. Or even fractions wouldn't be so bad, but there are other types of x-intercepts that a graph can have, which we'll do an example later on in the notes. But today we'll be learning about something called the rational zeros theorem. And that's really going to set us up for most of these problems. Now, remember what the word rational means. Rational just means a number that can be written as a whole number or integer, or a fraction. So anything like, for example, the number 2 is a rational number because it can be written as a whole number. The number 1/4 is a rational number because it can be written as a fraction. The number negative 7/96 is a rational number because it can be written as a fraction. Number 100, anything that's a whole number or a fraction is a rational number. Now if you're wondering what's not a rational number, well, we have imaginary numbers. Those are not whole numbers or fractions. And we have these, like the number pi. Pi is 3.14, but it continues on forever. There's no stopping point. It can't be written as a fraction because there's no stopping decimal point. It kind of goes on forever. So those are just some examples of irrational numbers. All right, so let's go ahead and move on to some examples. Now this rational zeros theorem is just the formal textbook definition of the rational zeros theorem. And this theorem is pretty useful. What it does, what it tells us is that you can take any polynomial function and using the constant, which is going to be called p. This might not make sense right now, but it will in a bit. And using the leading coefficient, which we call q, and listing all the factors of each, you can come up with a whole list of possible x-intercepts of your graph. So I'm going to go ahead and again, like I said earlier, I'm kind of jumping around because I had some of these examples out of order. So I'm going to go ahead and move up to, we're going to start with this example right here. It gives us a polynomial function, and it says, list the possible rational zeros of this function. Now, it doesn't say find the actual zeros. It says just list the possible zeros. Now, remember, zeros just means x-intercepts. So if this is throwing you off, you can go ahead and rewrite it as x-intercepts. So if I were to have a graphing calculator and I could graph this, I want to know what are all of the x-intercepts going to be. Okay. Now we're going to come up with a list of just possible x-intercepts, so not necessarily the actual x-intercepts, but a possible list of x-intercepts. And so what we can do is anytime we're given a polynomial function, a polynomial is anything with x cubed or higher, is all you have to do is locate the constant. The constant is the number without a variable, which in our case is -6, so that's our p-value. And identify your q value. That's the leading coefficient. That's the number, the coefficient in front of the exponent. That's the highest degree, which is this one right here. That's our q value. And what you're going to do using this rational zeros theorem is you're going to list the factors of p and then list the factors of q. So let's go ahead and do that out here. Let's start with the p value, which is -6. What are all of the things that go into -6? Well, 6 goes into 6. So I can list 6, and not just 6, I can list either a positive or -6, because positive 6 goes into -6 and -6 goes into -6. What else goes into -6? Well, 3 goes into -6, so I can list either positive or -3. Okay. Let's see, what else goes into 6? 2 also goes into 6, so I can also list positive or -2. And then lastly, a lot of people forget about this one, but 1 goes into everything. So you can also list positive or -1 will go into -6. So those are just all the things that go into 6. These are all the factors of p. And then what we're going to do next is we're going to find what are all the factors of q. Well, q is 2, so what are all the things that go into 2? Well, 2 goes into 2, so positive or -2 goes into 2. And then what else goes into 2? Well, 1 goes into everything, so positive or -1. So those are all the things that go into p, all the factors of p, and all the factors of q. This might not look like a list, but it is. We have pretty much a bunch of different combinations of numbers that we're going to make from this list. So let's go ahead and start with 6. Let's see. 6 divided by 2 is 3. So positive or -3 will go onto my list. We can also do 6 divided by 1. 6 divided by 1 is just 6. So I would add that to my list, positive or -6. Then we would take 3. 3 divided by 2. Well, 3 divided by 2 is 1.5. It's a decimal. You can write it as a decimal, or you can just leave it as a fraction. It's up to you. But I'll go ahead and leave it as a fraction. Positive or -3 halves. Then we have 3 divided by 1. Well, 3 divided by 1 is 3. It's already on my list, so I don't have to rewrite it again. Let's move on to 2 divided by 2. See how I'm just kind of making the list of all the possible combinations I can get from this. So 2 divided by 2 is 1 whole. So 2 divided by 2 is 1 whole, so I'm going to put plus or minus 1. 2 divided by 1 is 2, so positive or minus 2. Then I have 1 divided by 2. I know it's getting a little messy, there's lines everywhere. 1 divided by 2 is 1/2. So I can also add that to my list, positive or minus 1/2. And lastly, 1 divided by 1 is 1, but that's already on my list, so I don't have to rewrite it. So what I've done is I've come up with a list of all of the possible zeros, all of the possible x-intercepts. So I don't know what x-intercepts my graph actually has, but I know that some of these, or maybe even one of them or none of them, may be my x-intercepts of this graph if I were to graph it. But this is just a list of possible ones. We can go ahead and figure out which ones are actually x-intercepts on the next question. Okay. All right. There's a couple of questions on your homework assignment that just says list the possible ones, and so that's what you would do for those problems there. Okay. All right, so the next problem, example number 2, or I guess I relabeled it. It's the same exact equation, same exact polynomial, 2x cubed plus 11x squared minus 7x minus 6. It's the same exact function, except this time it doesn't say just list possible zeros. It says find the actual zeros, like what are they? So we have a list to choose from, like what are the actual zeros? Now I didn't say this earlier, but I should have. How many x-intercepts are there going to be? Well, there's going to be a total of 3 x-intercepts. And how do I know that? Because the degree is 3. So whatever the degree is, that's how many x-intercepts you're going to have. So we're going to have a total of 1, 2, and 3 x-intercepts. I mean, that's not what the graph will look like, but there's going to be a total of 3 of them. So what are those actual x-intercepts? What are the 3 x-intercepts? Well, the cool thing is we already have a list to choose from. So we have actually a total of 12 different possibilities of x-intercepts. So what we're going to do is we're going to test out each one of those 12 different numbers and see which of those are actual x-intercepts. So I'm going to go ahead and start with positive 3. I want to figure out, is 3 an x-intercept to this function or not? Now, you can go ahead, I'm going to do it once by hand, and then I'm going to use my calculator, so it might be useful to have a calculator for this. But in order to be an x-intercept, remember that's just whenever a graph crosses the x-axis, at every single x-intercept, the y value is 0. The y coordinate is 0. So if any of these are x-intercepts, we know the y value would be 0 at those x values. So let's say I plugged in the number 3 for x. So if I took my function, I plugged in the number 3. So I took 2, and instead of x cubed, I would plug in 3 cubed, plus 11, instead of x, I would plug in 3 squared, minus 7, instead of x, I would plug in 3, minus 6. And if the number 3 really is an x-intercept, I should get a y value, an output value of 0. I'm not sure if I will, but let's go ahead and test that out. I'm going to type that whole thing in. 2 times 3 cubed plus 11 times 3 squared minus 7 times 3 minus 6. And I got 126, so I know that that is not 0, so that's not an x-intercept. Okay. Then I would try out the next number, which was negative 3. And I would plug in negative 3 for x and see if I get an output value, a y value of 0. Because if I get a y value of 0, then I know it's an x-intercept. So I can go ahead and type that all in. 2 times negative 3 cubed plus 11 times negative 3 squared minus 7 times negative 3 minus 6. And that's a 60, which is not 0, so that's also not an x-intercept. Now you can go ahead and do this for every single number. Then we would plug in positive 6 and then negative 6, positive 3 halves, negative 3 halves, and so on, and that's fine. There's a nice little shortcut though. It'll save you some time. I can show you on the calculator. Is if you just go to y equals and you type in the function 2x cubed plus 11x squared minus 7x minus 6. So I just typed in the problem. And what you can do is you can go to your table by pushing second graph. And you can look through this list and see which of these numbers will give you a y value of 0. Now, we can look at negative 3. We got 16, so we know that's not it. We can look at positive 3. We got 126, just like the calculator says. You know that that's not it. However, what about all these fractions? How can I figure out what about the fractions? Well, the fractions are not written on here, but there is a way to find them. What you can do is you can tell your table or tell your calculator to put it in ask mode, so push second window, and you see how this first row says auto? Change it to ask. Move it over to ask and push enter. And now ask is highlighted. All right, go back to your table, and it should be empty because you might be wondering, where did all the numbers go? Well, you're just telling the calculator you want it to ask specific x value. So I'm going to plug in the number 3. I already did it, but I'm going to plug in the number 3, enter. It gives me 126. That's not 0, so it's not an x-intercept. I'm going to plug in the number negative 3 for x. It gives me 60, which I know it's not it, so that's not an x-intercept. Let's try positive 6. It gives me 780, so that's also not an x-intercept. I want a y value of 0. Let's try negative 6. Hey, negative 6 gave me 0, so I know that negative 6 is an x-intercept, aka 0, if you want to call it a 0. So negative 6 is one of the x-intercepts. There should be 2 other ones because we have a total of 3. All right, let's go ahead and try the rest of the numbers. Positive 3 halves gave me 15, which is not 0. Negative 3 halves, that's not 0. This is a much quicker method. I plugged in the number 1. I got 0, so I know 1 is also an x-intercept. It's a much quicker method than having to type in each one and plug in each one by hand. All right, negative 1, I got 10, that's not it. 2, nope. Negative 2, no. 1/2, no. And negative 1/2. There you go. Negative 1/2 also gave me a y value of 0. So there are our x-intercepts. And there we go. So we have 3 x-intercepts, negative 6, 1, and negative 1/2. If you wanted to make a sketch of this, it would probably look something like this. Here's negative 6 on the x-axis. Here's negative 1/2. Here's positive 1. So the graph might not be perfect. It's probably going to look something like this, because it's going to have those 3 points on the graph. And what do you know? Yes, it does. Okay. All right, so that's pretty much what we're going to do for the next few problems. Just going to get some more practice with that. Okay. All right, so let's move on to the next one. This next example says list the possible rational zeros of this function. Now, this rational zeros theorem says that if you just identify the p-value, which is the constant, which in our case is negative 2, and you identify the q-value, which is the leading coefficient, which in our case is 15, and you list all the factors of each one, you can come up with a list of possible x-intercepts. Now, how many x-intercepts are there going to be total? Well, there's going to be 3 x-intercepts. And how did I know that? Because the degree, the highest exponent, is 3. So there's going to be a total of 3 x-intercepts that this graph will have. There will be 3 answers. All right, let's go ahead and start by listing all the factors of p. So the factors of p, negative 2, what all goes into negative 2? Well, negative 2 goes into negative 2. So positive or minus 2 goes into negative 2. What else goes into 2? 1. 1 goes into everything, so positive or minus 1. All right, that's pretty much it. Now let's look at 15 and think of all the things that go into 15. Well, 15, positive or negative 15 goes into 15. 5 also goes into 15, so positive or negative 5. 3 also goes into 15, so positive or negative 3. And lastly, 1 goes into 15. 1 goes into everything, so positive or negative 1. So I've listed all the factors of p, listed all the factors of q. Make sure that p is always on the numerator, q is always on the denominator. And then you're just going to write down all of the combinations of each of these numbers. So let's go ahead and start with 2. 2 divided by 15. That's a decimal. It's a fraction. It doesn't even simplify, so I'm just going to leave it as positive or negative 2/15. All right, then I'm going to go ahead and combine 2 divided by 5. That's also a fraction. It doesn't simplify, so I'm just going to leave it as 2/5. Next one is 2/3. 2 divided by 3 is 2/3, so I'll just add that to the list, positive or negative 2/3. And then 2 divided by 1. 2 divided by 1 is just 2, so positive or negative 2. Okay. All right, now we're going to go ahead and move over to the other numerator, which is 1, and list all the combinations that we can make. So we have, let's see, we have 1 divided by 15, which is just 1/15. That doesn't equal a whole number, just a fraction. And then we have 1 divided by 5, which is just 1/5, so positive or negative 1/5. And then we have 1 divided by 3, which is just 1 divided by 3, 1/3. And lastly, 1 divided by 1, which is just 1. This is a much bigger list than the previous one, but that's okay. There's a bunch of different numbers to choose from, but this is the list of all of the possible rational just means whole number or fractions, x-intercepts, aka 0, if you want to call it zeros instead. So we come up with a list of the possible x-intercepts. Now there's a total of 3. We don't know which 3 those are, but we know that some of them are probably in this list somewhere. All right, the next problem is the same exact polynomial function, except this time it doesn't say list the possible rational zeros. It says actually find all of the zeros of this polynomial function. So what we're going to do is, just like the previous problem, we're going to go ahead and test out each of these individual numbers and figure out which of these are actual x-intercepts. Now again, you can plug each one in by hand, starting with the first one. So you can plug in positive 2/15 for x, and you would have 15 times 2/15 to the third power, plus 14 times 2/15 to the second power, minus 3 times 2/15 minus 2, and see if you get 0. And if you do, it's an x-intercept. If you don't, then it's not. That's going to be a lot of work to do by hand, individually, because there's so many different numbers. So I'm going to use this calculator shortcut to help me speed up the process. I'm going to go to y equals, type in the actual polynomial function, which is 15x to the third plus 14x squared minus 3x minus 2. So I've typed in the problem, and now I'm going to go to the table. Now, you can actually, if you don't like having these numbers, you can delete them. My calculator is already in ask mode. If yours is not, you can make it go to second window and change that first auto to an ask. But if you want to get rid of these numbers, you can always just push delete, and it'll delete them one by one if you want a clear table. Okay, let's go ahead and start with the first number, 2/15. So I would just type in 2 divided by 15, push enter. That's not 0. Negative 2/15, that's not 0. I'm just kind of going down this list. Let's try positive 2/5. That is an x-intercept, so 2/5 is an x-intercept. I know there's at most 2 more. Let's try negative 2/5. That's not 0. Next, let's try positive 2/3. Nope. Negative 2/3. No, we didn't get a y value of 0. Positive 2. No. Let me try negative 2. That does not work either. You can kind of cross them out as you go along and try them, but those do not work. Let's try positive 1/15. All right, mistype that in. And that is not 0. Let's try negative 1 divided by 15. That is not 0. 1 divided by 5 is not 0. Negative 1 divided by 5 is not 0 either. Let's try 1 divided by 3. Nope. Negative 1 divided by 3, I got 0, so I know negative 1/3 is also an x-intercept. All right, I just need to try positive and negative 1. So let's try 1. That's 24. Let's try negative 1. Yeah, negative 1. And I got 0. So we have a total of 3 x-intercepts, or zeros if you want to call them, and they are 2 fifths, negative 1/3, and negative 1. And if you want, you can kind of make a little sketch. You know, the graph's going to look something like this. Here's negative 1. Here's negative 1/3 somewhere. Here's positive 2 fifths. It's going to have these 3 points on the graph. And you could probably, I'm not sure what they look like, but maybe something like that. And there we go. Okay. All right, moving on. All right, let's do one more example just like the previous 2, and then we'll move on to a little bit more of a challenging one. All right, the next example, it gives us a polynomial function. Now this one doesn't even say list the possible zeros. It just jumps straight into saying find the actual zeros. What are they? But we're going to use the same process as what we've been doing. This is the polynomial function. So let's go ahead and start by using the rational zeros theorem. So let's first identify what is p. Well, the p value is the constant, which is -6. And the q value is the number in front of the highest degree. Now, x to the 3rd power, that's the highest exponent. There's no number in front of it. There's no coefficient. It's clearly written, but if we wanted to put a number, it would be the number 1. So our q value is 1. So let's start by listing all of the factors of p and all of the factors of q. So let's see, all of the factors of p, what numbers go into 6? Well, 6 goes into 6, so we can list positive or negative 6. 3 goes into 6, so positive or negative 3. 2 goes into 6, so we can list positive or negative 2. And don't forget 1. 1 goes into everything, so positive or negative 1. And then let's list all of the factors of q. Q is just 1, so what all goes into 1? Well, there's only one thing that goes into 1, that's positive or negative 1. Okay. All right, we have a combination of numbers that we can make. Let's go ahead and list all of the combinations. Let's start with 6. 6 divided by 1 is just 6, so positive or negative 6. Then we have 3 divided by 1. 3 divided by 1 is just 3, so positive or negative 3. 2 divided by 1 is just 2, positive or negative 2. And then 1 divided by 1 is just 1, so positive or negative 1. And that's all of the possible x-intercepts. So this is the list of possible zeros or possible x-intercepts, however you want to call them, for our polynomial function. Now, how many x-intercepts are there going to be total? Well, there's going to be 3 x-intercepts total, and the reason I know that is because whatever the degree is, which in our case is 3, that's how many x-intercepts there will be. Okay, now we have to figure out which of these numbers are actual x-intercepts. So let's go ahead and start by testing out each one. Now I'm going to use the calculator for this again, and I'm just going to jump straight into y equals and type in my original function, which is x cubed plus 2x squared minus 5x minus 6. And I'm going to go to my table, second graph. Now my calculator is already in ask mode, but if it's not, make sure that you change it to ask mode by going to second window and making sure that first row is in ask mode. All right, I'm going to go ahead and test out each one of these. If I plug in an x value of 6 for x, will my y value be 0? That is not true. So I will go ahead and try negative 6. Let's see, if we plug in negative 6 for x, will the y value be 0? Nope. Let's try positive 3. When x is 3, the y value is not 0. When x is negative 3, the y value is 0. So that's one of our x-intercepts, or zeros, is 3. Oh, sorry, negative 3. Let's try positive 2 now. When x is 2, the y value is also 0. So that's also an x-intercept. When x is negative 2, the y value is not 0. When x is 1, the y value is not 0. When x is negative 1, the y value is 0. So those are my 3 x-intercepts. And I know that I have found all of the x-intercepts because there's 3 of them. Let me circle the whole answer. And there's our answer. Okay. All right, most of the problems on your homework assignment is like that. So we're going to go ahead and do one more problem. And this one is a bit of a challenge. Okay. Now remember in the beginning, I did say that it's nice whenever all of our answers are whole numbers or integers. We've been using something called the rational zeros theorem to find all of the x-intercepts that are either whole numbers or fractions, just like these two right here. However, not all polynomials have pretty x-intercepts like those all did. Sometimes they have x-intercepts that are imaginary, that you can't even see on a graph. Or sometimes they might have x-intercepts that are irrational, like numbers that go on forever that can't be written as a fraction, like the square root of 2, that doesn't have a stopping point to it. So in those cases, how would we find those x-intercepts? So in cases where all of the zeros are not rationals, what would we do then? So that's what we're going to do for our last example. And I'm going to use this one right here. There we go. Okay. So let's go ahead and start with this next example, which is negative x to the 4th power plus 3x squared plus 4. Now, first thing it says is just list the possible rational zeros. So just like we've been doing, I'm going to go ahead and first start by identifying what is p, which is the constant, which is in our case is 4. And our q value is the number in front of x, which is, well, it's not written, but it's negative 1. All right, I'm going to go ahead and list the possible combinations or factors of p and q. So the factors of p, which is 4, is what numbers go into 4. Well, 4 goes into 4, so positive or negative 4. 2 also goes into 4, so positive or negative 2. 1 also goes into 4, so positive or negative 1. And that's about it. As far as q, well, q is negative 1. There's only one number that goes into negative 1, and that's 1, so positive or negative 1. Okay. And then what we're going to do is we're going to list all of the combinations of numbers we can make from this list. So let's start with 4. 4 divided by 1 is just 4, so positive or negative 4. All right, 2 divided by 1 is just 2, so positive or negative 2. And then lastly, 1 divided by 1 is just 1, so positive or negative 1. So what we've done is we've come up with a list of possible rational, meaning whole number or fractions, x-intercepts. Okay, these are not necessarily all x-intercepts. We've got to test out which ones of them are. So the next problem, it's the same exact polynomial, except this time it says, what are the real zeros? What are the actual x-intercepts? Okay, so I'm going to do what we've just been doing the previous two problems. I'm going to go ahead and test out each one. Now, before I do that real quick, how many x-intercepts are there going to be total? How many answers should we have total? We should have a total of 4 x-intercepts. And how do I know that? Because the degree, the highest exponent of x is 4. So I know that there should be a total of 4 x-intercepts. So let's go ahead and test out each of these numbers. There's a total of 6 choices, and see which of them are actual x-intercepts. So I'm going to go ahead and use a calculator table to help me with that. I'm going to go to y equals and type in this problem. Negative x to the 4th power plus 3x squared plus 4. I'm going to go to my table. I'm going to delete all this. Delete, delete, delete. All right, let's test out each one. Positive 4. Nope, does not give me a y value of 0. Negative 4. No. Positive 2, yes, positive 2 is an x-intercept. All right, what else? Let's try negative 2. Negative 2 is also an x-intercept. All right, positive 1, no, and negative 1, no. So I only got 2 x-intercepts from this list. There should be a total of 4 x-intercepts. There should be a total of 4 answers. However, I only got 2 answers from my list. There should be a total of 4. So where did we go wrong? Well, remember, like I said earlier, not all your answers will always be rational numbers, meaning whole numbers. So this little theorem that we've been using, this is where we list out the factors, that only tells you all the possible rational x-intercepts. What if you have x-intercepts that are imaginary or irrational? Well, you can't use that theorem. But what we could do is we can go ahead and take out these two zeros by synthetic division or long division to help us figure that out. So what I'm going to do is I do know that this was the function that we started with, and I already know that 2 and negative 2 are both x-intercepts of this. I know that 2 is an x-intercept and so is negative 2. So if I take these two x-intercepts or factors out, what will I be left with? So what I mean by that is if 2 is an x-intercept, then that means that x minus 2 is a factor. If negative 2 is an x-intercept, this means that x minus negative 2, which is just x plus 2, is also a factor. It goes into it evenly. So what I'm going to do is I'm going to take this original problem that we have. I'm going to go ahead, first off, I'm going to rewrite it as this. Negative x to the fourth plus 0x to the third, just because there is no x to the third, so I just want to make sure I kind of have all the x's accounted for, plus 3x squared plus 0x because there is no regular x, plus 4. I just like to make sure that I have all of them, x to the fourth, x to the third, x to the second, x, and then a number going in order. I didn't change anything, I just rewrote it like that. So there are 0 x cubes and there's 0 x's. All right, and what we're going to do is we're going to go ahead and take our problem and we're going to divide out each of these factors. We're going to take out each of these factors, basically factor out each of these x-intercepts and see what we'd be left with and see if it's easier to tell by then. So I'm going to divide this function by each of these. We can use synthetic division just because it's a little easier, so I'm going to do that. So the way we'll go ahead and start with this first factor, or this first x-intercept. So I'm going to go ahead and I'm going to start by making this backwards L, and the number that goes in it is going to be 2. And then my numbers that will go on this first row will be all the coefficients. So starting with x to the fourth, it'll be negative 1, then 0, then 3, then 0, and then 4 again. All right, I'm going to go ahead and start by bringing down the first number, which is negative 1, and then it's like a multiply, add, multiply, add, multiply, add process. We covered synthetic division a couple classes ago. So negative 1 times 2 is negative 2, and then add. 0 plus negative 2 is negative 2. Multiply again, negative 2 times 2 is negative 4, and then add. 3 plus negative 4 is negative 1. Multiply negative 1 times 2, and we get negative 2. And then you add. 0 plus negative 2 is negative 2. Multiply again. Negative 2 times 2 is negative 4. And then we add. 4 plus negative 4 is 0. This last number is always your remainder, which makes sense. 0 should be a remainder because we knew that 2 should go into it perfectly. X minus 2 should be a factor. It should go into it perfectly because it's an actual x-intercept. So what we did is we took our original function and we divided it by x minus 2. And so what we're left with now is our function, or f of x, if you don't want to write y, equals x minus 2 times, and then we would convert this into equation form. So negative 1, you don't have to write the 1, x to the third power, because our problem originally started with a 4, and whenever you divide using synthetic, your answer will be 1 less than that. Minus 2 x to the second power minus 1x minus 2. So what I've done is I have this original problem is the same exact equation as this. I just wrote it as x minus 2 times this. And if I were to multiply this out, I would end up with the same original problem. Okay, these two equations, these two functions are equivalent. If you want to FOIL everything out, you will get this original problem. I'm just kind of dividing out to take out one of the factors. Okay. All right, so I've taken out one of the factors, one of the x-intercepts. Well, we have another x-intercept, which is negative 2, so we can divide again to kind of decrease this and kind of work with it easier. So I'm going to do synthetic division once again, except this time I'm going to take out the x-intercept negative 2. So that's the number that's going to go in the backwards box. And then I'm going to write down all of the coefficients of pretty much what I left off with, which would be negative 1, negative 2, negative 1, negative 2. Pretty much negative 1, negative 2, negative 1, negative 2. And I'm going to do synthetic division once again. Start by bringing down the first number, and then multiply, add, multiply, add, multiply, add. So negative 1 times negative 2 is positive 2. And then you're going to add the columns up. Negative 2 plus 2 is 0. 0 times negative 2 is 0. Negative 1 plus 0 is negative 1. And negative 1 times negative 2 is positive 2. And then add. Negative 2 plus 2 is 0. This last number is always your remainder, which makes sense. We should have a remainder of 0 because it should go into it perfectly. Okay. And what this tells me is I can now write my function as f of x equals x minus 2 times x plus 2, because I just took out the factor x plus 2. I did synthetic division. I divided that out. And I am now left with, well, this is what I'm left with. If I change it back to equation form, this would be negative 1, you don't have to write the 1, x to the second power, because the problem originally was x to the third, so your answer will be 1 less power. Plus 0x, you don't have to write plus 0x unless you really want to. You can. And then minus 1. Okay. That's where I got this answer. So keep in mind that this function is the same exact function that we started with in the problem. It's also the same as this. This is just factored out. I'm kind of factoring it out using synthetic division. If I were to multiply and FOIL everything out, all of this using the box method or FOIL, you would end up with this original problem. Okay. So what I've done is I've taken this function and I've factored out an x minus 2 and an x plus 2. And the reason why I did that is because I know two of the x-intercepts. One of them is an x-intercept is 2. Another x-intercept is negative 2. And I know that there's two more answers because remember we said there's 4 x-intercepts. So what are the last two? Well, the last two are going to come somewhere from here. Now this is a quadratic because it's x squared. Anytime you want to find zeros or x-intercepts from a quadratic, you can either factor or use the quadratic formula. Now, the quadratic formula is just where you label A, B, and C, and you could plug it in to the quadratic formula, which is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. You can go ahead and try to factor. I don't think this one will work just quite right for this one. But I'll go ahead and use the quadratic formula to go ahead and just factor out this last two parts. I want the whole thing to be in factored form. So my quadratic formula will look like this. X equals negative b, which b is 0, plus or minus the square root of b, which we said was 0, squared, minus 4 times a, which a is negative 1, times c, which is negative 1, and the whole thing is over 2 times negative 1. Because a is negative 1, b is 0, and c is negative 1. And then I'm going to go ahead and I'm going to figure out what this equals. You can go ahead and try to type in the whole thing. You might get a few errors, so I'm going to go ahead and do it piece by piece. Negative 0 is just 0. You can go ahead and just get rid of that. Plus or minus the square root of 0 squared. I'm going to type in everything inside the square root. 0 squared minus 4 times negative 1 times negative 1, which is negative 4. And the whole thing's divided by 2 times negative 1 is negative 2. I'm kind of working this out by hand because if you try to type in the whole thing, you will probably get an error. It won't let you calculate it. Alright, once I finish doing this math, I will have positive or negative. Now the square root of negative 4, what is the square root of negative 4? Well, you can't take the square root of a negative. We know that the square root of 4 is 2, but what about the negative? Anytime you try to take the square root of a negative number, you pretty much just have imaginary numbers. So the square root of negative 4 is 2 I. And then the bottom was, the denominator was negative 2. Okay. That's why you won't be able to calculate it on your calculator. Now let's see, what is this? What's positive or negative 2 divided by negative 2? Well, you're just going to have positive 2 divided by negative 2, which is just negative 1. So you're going to have two answers. You're going to have negative 1i, or you could just put I. And the second option will be, because the two pretty much cancel out, you'll have negative divided by negative, which is a positive I. And so those are our other two x-intercepts. So we have now found all of the x-intercepts. One of them's 2, one of them's negative 2, one of them's negative I, and one of them is I. There's a total of 4, so those would be our 4 x-intercepts. If you want to write it in factored form, you could. X minus 2, x plus 2. This would be x plus I, x minus I, just because I wrote it all in factored form instead. But that just means that you have a total of 4 x-intercepts. Positive 2, negative 2, negative I, and positive I. Those are our 4 x-intercepts, or zeros. This one was a bit of a tough one. This one's a challenge one. Most of them are not like this, but in special cases, I think there might be just 1 or 2 problems on your homework that have you do this, so I just wanted to go over at least one. And that's it.